This video is the first half of a practice test from Unit 2 of AP Calculus. In this video, we will practice our differentiation techniques, and we will explore the graphical relationship between an original function f and its first derivative f prime and its second derivative f double prime. For the next few problems, we need to find the derivative and match it with the multiple choice options. For problem number 1, I can tell this is going to be a chain rule problem. We actually will have to use the chain rule twice because this is a function within a function within a function. Let me rewrite the problem to make it more obvious. When you have cosine squared like this, it really means that you're squaring the entire cosine function. So that in red is the outer function. And then cosine is sort of the middle function. And then inside of cosine, we have pi x. So we have the red outer function, the blue middle function, and the purple inner function. According to the chain rule, we need to start by taking the derivative of the outer function. So using the power rule, I'm going to put the 2 in the front. I reduce the power by 1, and there it is. When you do the outer function, you leave the inner function the same. So I have cosine and then pi x. But then you must multiply by the derivative of the inner function. So again, I need to start with the outer part of the inner function. So I'm going to multiply by the derivative of cosine. We know that the derivative of cosine is negative sine. So we're going to be multiplying by negative sine. At this point, you leave what's inside the same. So I will put negative sine pi x. But then you once again have to multiply by the derivative of the inner function. So the derivative of the purple is pi. So this is the derivative. I just have to match it with the right multiple choice option. So maybe a little simplification is in order. We have the 2 and the negative sign and the pi. So we can write negative 2 pi and put that in the front. Then we have the sine and the cosine. Looking at the answer choices, they always seem to write the sine function first. So I will do that as well. So we have sine of pi x times cosine of pi x. So this would be our answer, which matches up with option B. So that's the answer. For number 2, it looks like it's time for the quotient rule. So here is the quotient rule poem. Low D high, less high D low. Draw the line and down below, the bottom squared will go. Notice that when I say D high, that means the derivative of the top part of the function, and D low means the derivative of the bottom part of the function. So let's do it. So y prime equals low D high. So low means just write down the bottom part the way it is. So there's low. D high means let's do the derivative of the top part. The derivative of sine is cosine. And then we have the constant, but the derivative of a constant is nothing. So that's D high. Less means subtraction. So low D high less high, which means just write down the top part as is. So I have sine x minus 1. Low D high less high D low. So it's time for the derivative of the bottom part. The derivative of cosine is negative sine. low d high less high d low. Draw the line, and down below, the bottom squared will go. So cosine squared goes in the bottom. This is the answer, but we have these multiple choice options that we must match. So some simplification will be required. Obviously, cosine times cosine will be cosine squared. And then we've got this negative sign in the middle, but also we're multiplying by negative sign. Let's go ahead and do negative times a negative to make a positive. In other words, I'm taking this negative sign and I'm going to bring it out in the front, which will cause this to become plus. So that's going to leave us with this for a moment. So we've got sine x minus 1, and then we've taken the negative sign away, so we just have sine x sitting here for a moment. But on my next move, I am going to do the distributive property from the right-hand side. So sine x times sine x will give me sine squared x minus, and then of course sine times 1 is just sine x. But right now your identity alarm is going off because you see the most famous identity, the Pythagorean identity. Cosine squared plus sine squared is equal to 1. So let's make that substitution. So we are left with 1 minus sine x over cosine squared x, which matches option B. This is the graph of function f. We will use it to justify our answers to the next few questions. When you justify your answer, remember to avoid ambiguous terms like it, or the graph, or the function. Instead, you will be very specific and say things like, function f is negative at x equals 2. Also, if I ask you about a function that is not shown, for example, if I ask you something about f prime, you have to base your answers on function f since that's the only graph that we have. For example, you would say something like, because function f is decreasing at x equals negative 5, f prime is negative. Here's a chart summarizing the key relationships between the graphs of the original function f compared with f prime and f double prime. Make sure you have this information memorized. If I were you, I would write this chart very quickly at the beginning of your next quiz or test in the margin. Problem number 3. At x equals negative 1, is f prime increasing, decreasing, or neither? We want to know if f prime is increasing or decreasing, but we have to base our answer on the original function f since that's the graph that we have. If f is concave up, then f prime is increasing. If f is concave down, then f prime is decreasing. At x equals negative 1, f is concave down. Therefore, f prime is decreasing. So let's justify our answer. We would say decreasing because f is concave down at x equals negative 2. This is really the only justification that would be accepted. Notice how I had to base my justification on function f because that's the graph that I'm given. I didn't say anything about f prime. Also, notice that in my description, I stuck to the descriptions that are on this chart. Concave up, concave down, increasing, decreasing, positive, negative. Those are really the only things that should appear in your justification. Number 4, is f prime at 5 positive, negative, 0, or not defined? So they're asking us about f prime, but somehow we have to base our answer on function f. Let's see, f prime will be positive if f is increasing. F prime will be negative if f is decreasing. At x equals 5, which is right here, we see that f is increasing. Therefore, f prime is positive. Let's justify our answer. We would say positive because f is increasing at x equals 5. And this is really the only acceptable justification. Number 5, find a value of k for which the following statement is true, or explain how you know that no such k exists. For problems like this, I like to start with my justification and then look for the value of k that fits the justification. So the first part says f prime is less than 0. In other words, f prime is negative. They're asking me about f prime, but somehow I have to base my answer on function f because that's what I'm given. So we know that f prime will be negative if f is decreasing. We will fill in the blanks later, but k equals blank because f is decreasing at x equals blank. Now, the other piece of information is that f double prime is equal to 0. So that means that f double prime is neither positive nor negative. So that means that function f is neither concave up nor concave down. So we will add, and f is neither concave up nor concave down at x equals blank. So now we just need to look back at the graph and hunt for an x value where f is decreasing while neither concave up nor concave down. Let's start with decreasing. Let's highlight the intervals where f is decreasing. These are the parts of the graph where f is decreasing. It's going downhill from left to right. Now, where's f neither concave up nor concave down? That means linear. So let's highlight the parts of the graph where f is linear. So my blue highlights show the parts of the graph where f is neither concave up nor concave down. So we need to pick a k value where both of these are true at the same time. So you can see that the interval from negative infinity to negative 4, this is where the function is both decreasing and linear. Decreasing and also neither concave up nor concave down. So we just need to pick an x value from this green interval. So how about negative 5? So we could say k equals negative 5 because f is decreasing at x equals negative 5 and f is neither concave up nor concave down at x equals negative 5. Of course, I could have also picked negative 6 or negative 7, etc. For the next few problems, we will again answer questions and then justify. However, be careful, even though this graph looks the same, this is now g prime, the derivative of some function g. Number 6, at x equals negative 4, is g of x increasing, decreasing, or neither? So notice, they're asking about g of x, but somehow we have to base our answer on g prime, since that's the graph we're given. So we want to know if g is increasing or decreasing, but we know that g will be increasing when g prime is positive, and g will be decreasing when g prime is negative. Looking at the graph of g prime, at x equals negative 4, we see that g prime is negative. Therefore, g of x is decreasing. Pause the video and see if you can write the justification. You should have written decreasing because g prime is negative at x equals negative 4. Number 7, at x equals 5, is g of x concave up, concave down, or neither? So they are asking us if G is concave up or concave down, but we have to base our answer on G prime since that's the graph we're given. Well, G will be concave up if G prime is increasing. G will be concave down if G prime is decreasing. At x equals 5, we see that G prime is increasing. Therefore, G is concave up. Pause the video and see if you can write the correct justification. You should have written concave up because G prime is increasing at x equals 5. And this is really the only acceptable justification. Number 8, find a value of k for which the following statement is true, or explain how you know no such k exists. At x equals k, the graph of G is decreasing and concave up. Let's write the justification first, and then we will fill in the blank with the correct k value later. Let's start with this part. The graph of G is decreasing. Under what circumstances will G be decreasing? Well, they're asking us about G, but we have to base our answer on G prime. So G will be decreasing when G prime is negative. So we write k equals blank because G prime is negative at x equals blank. But also we want G to be concave up. But again, they're asking us about G, but we must base our answer on G prime since that's the graph that we have. G will be concave up when G prime is increasing. So we add, and G prime is increasing at x equals blank. So now we just have to look back at the graph for an x value where G prime is both negative and increasing. Let's start by highlighting the parts of the graph where G prime is negative. This is the part of G prime that is negative because it is below the x-axis. Now let's highlight the parts of the graph where G prime is increasing. Here are the parts of the graph where G prime is increasing because it's going uphill from left to right. So we need to choose our k value from the areas that are both negative and increasing. So for example, a good k value would be -3. Another one would be +4. So filling in the blanks, we could say that k equals -3 because G prime is negative at x equals -3 and G prime is increasing at x equals -3. We also could have said the same thing for k equals 4. By the way, I keep choosing integers like -3 and 4, but I could have just as easily used a decimal like k equals 3.71 or something like that. Number 9, on the axes above, sketch a possible graph of function g. Regardless of whether you are given g and you are asked to graph g prime, or if you're given g prime and you're asked to graph g, the first step is to divide the graph into intervals of increasing and decreasing. We can see that G prime is decreasing in the blue intervals and increasing in the yellow interval. In one interval, G prime is neither increasing nor decreasing. But we are supposed to graph function g, so we need to translate this information into information about function g. If G prime is increasing, then G will be concave up. If G prime is decreasing, G will be concave down. So function g will be concave down in the blue intervals and concave up in the yellow. In this interval, g will be neither concave up nor concave down. In other words, g will be linear in this interval. Going from g prime to g is a two-step process because now we must divide g prime into intervals of positive and negative. Where is it above the x-axis and where is it below the x-axis? G prime only crosses the x-axis twice. So it starts out positive, and then in this middle interval it is either less than or equal to 0, and then in the final interval it is positive. But we are trying to graph function g. So what we really care about is wherever g prime is positive, g is increasing. Where g prime is negative, g is decreasing. So function g will be increasing in the yellow intervals and decreasing in the blue interval. There's one more piece of information that we need in order to sketch the graph of function g. Where is g prime equal to 0? Remember that g prime is the slope of function g. So wherever g prime is 0, the slope is 0. The slope will be 0 here, here, and here then. If the slope is 0, that means we have a horizontal tangent line at these x values. Now we are ready to sketch the graph of g. At this point, my goal is to create a new interval every time something changes. If we go from concave up to concave down, that's a new interval. If we go from increasing to decreasing, that's a new interval. So I'm just putting new intervals all over the place, wherever something changes. So I can start my graph of function g at any height that I want, but in this first interval, g should be increasing and concave down. Also, this little purple line reminds me that g should end at a horizontal tangent line. So here I go, increasing and concave down, and ending at a horizontal tangent line. In the next interval, we are decreasing and concave down. No horizontal tangent line required. So decreasing and concave down. In the next interval, we are still decreasing but concave up and ending at a horizontal tangent line. So here we go, decreasing but concave up and ending at a horizontal tangent line. In the next interval, we are still decreasing but concave down. No horizontal tangent line. So here I go, I'm decreasing but concave down. I can see that I am running out of space at the bottom of this graph. So I wish I had made this graph higher. So I'm going to actually raise this up a bit. In this next interval, you will see why I had to raise the graph up so much. Because the function g should now be decreasing and linear. But focus on that linear part. We can be more specific than that. We see that g prime is horizontal here at -2. That means the slope during this interval is exactly -2. So I'm just going to write that down. The slope is equal to -2. So when I draw function g, I should draw it so that the slope is -2, which means that it should be going down 2 over 1, down 2 over 1. So you can see how much space I needed to accomplish this. So this should be linear, but it should be like this, down 2 over 1, slope of -2. And in the next interval, it is still decreasing, but concave up. And also, it should end at a horizontal tangent line. So here I go, decreasing, but concave up, and ending at a horizontal tangent line. In the last interval, g should be increasing and concave up. So here you go. This is a pretty good sketch of a possible function g. That's enough for one video. For the second half of this practice test, watch the next video.